Today I would like to discuss field theories in the form of path integrals. So we will have path integral formulation of field theories. And we want to constrain ourselves where we have just additive noise. It's possible to do this for multiplicative noise as well, but this is just the simpler case. So, and the reason to do that is because those path integrals are the basis for perturbation theory, and especially in critical phenomena. So when you want to do dynamic RG, then this is the way to go. We will not really consider RG, as I said. Another reason for studying path integrals is you can actually prove fairly straightforwardly general relations. And among those general relations, what we'll have is the so-called fluctuation dissipation theorem. And that's a theorem that relates response and correlation functions. We have seen simple examples for that. And another one is what's called work theorems or fluctuation theorems. And this is a more recent development which started with the work of Szarzyński and Gavin Crooks. And Udo Seifert has quite beautiful review articles on this and also a lot of really fascinating work. So work of fluctuation theorems, and that goes under the name of stochastic thermodynamics. Okay. So what would we like to focus on? So here we look at a set of fields, phi alpha, and we do have Langevin equations for that. And let me write them in a rather general form. Say we have some functional that I call A alpha. That's a function of these fields. So in general of all the fields in this vector field. And then we have a noise, theta alpha, that also depends on space and time. And so does the fields that we consider here. They are space and time dependent. So what do we have in mind? We have in mind, for example, that our A alpha is something like minus L alpha df with respect to d phi alpha. That's model A. Or we could also have that our A is something that comes from model B, and now let me write it for a scalar. So A may also be the gradient of a constant mobility times the gradient of a chemical potential, so df d phi, and that's then a simple example of model B. Okay. And I'm assuming that L alpha and also the m are constants. If I wouldn't have that, right, I would have multiplicative noise, and that's what I don't want here. So for the noise, what we take is Gaussian white noise, and that has the mean is 0 for all the components, and the variance we take as zeta alpha at positions x and t, zeta beta at position x prime and t prime is given by a noise amplitude, a matrix of noise amplitudes times short range correlations in space and short range correlations in time. And these n alpha betas, they are assumed to be constants, and that's what it means that we have additive noise. Right? So I hope it's clear so far. Now, our goal is that we would like to have a probability distribution function for the fields and write some kind of probability measure that then characterizes these fields. And that's going to be the path integral formulation. We have seen that before for the case of a dynamics of a particle. Now we do the same thing for fields. So what we want is we want to have a map of the probability distribution for the noise, zeta, and we want to translate this into a probability distribution. The point needs to be, right, this is a function of space and time, so I need a probability distribution function for the fields, which are also functions of space and time. That means our starting point will be the Gaussian white noise for our Langevin noise. That means we, instead of correlation functions, write a probability distribution function for our Langevin noise, which is some normalization constant that I don't care about here too much, because in the end we need to normalize it such that probabilities are, when they're integrated, giving a 1. And what we have here is the usual Gaussian distribution with integrals over time. And now note that this is over a time window. I'm observing my stochastic process for the window from time t0, some initial time, to some final time tf. And I'm integrating over space. And in general, this will be a d-dimensional space. And then I have zeta alpha of x and t, the noise amplitude matrix taken as its inverse, times zeta beta of x and t, where in this notation I'm implying some convention, so I'm summing over all repeated indices that appear there. Okay, if you want to make this explicit, you can also write here a sum over alpha and beta, but you don't have to if you use some convention. And as said, I want this such that I'm getting a 1 if I'm integrating over the corresponding measure of this functional integral, measure being defined in the same way as before. You discretize and then you get a proper integration measure in the discretized form, and this has to be 1. That's simply the normalization of our probability density. All right, now before we go and derive the functional for the probability distribution of the field, let me make a short note on discretization. And again, this is just what we did have before for a particle, just now for fields. So we discretize time, and we do this such that we take time points t mu, which is the initial time point plus integers mu times a time increment delta t. And mu is an element from 1 up to some number. Let me call this then, to not compare. It's n here, but don't worry, this is not the same n as the noise amplitude, just the number of sites that we have along the discretization path. And then what we can do is we write the Langevin equation in a discretized form. Now we have 2 indices. The first index alpha stands for the component of the field. You can also read into that the corresponding index for spatial position. And then on the left-hand side, I need to take the difference between 2 time points, mu and mu minus 1, and divide by delta t. And then on the right-hand side, we have a choice. We can use a arbitrary constant theta between 0 and 1 to discretize the first term, 1 minus theta a alpha mu minus 1. So for example, if you choose theta equal to 1, then you just have the first term. If you choose it to 0, you just have the second term. And that's an arbitrary choice you can make. And here we do have the noise evaluated at time t mu. Okay. And that's important to keep in mind, because when we change variables, this expression here tells you how to actually calculate the Jacobian. So this is important for calculating the Jacobian. Good. Now, let me write out what we do get when we perform this kind of integral. So the starting point to map the probability distribution function of the noise to the probability distribution function of the field is the fact that there's a one-to-one mapping between the two. For each noise trajectory, there is a field trajectory. So if I take the probability density and multiply it by the corresponding measure for such a trajectory, then this probability that you have here must be the same as the probability that you do have for the fields. Now for the field variables as a function of space and time, it's also a functional. And here I do the same thing, multiply by the corresponding measure of a trajectory phi. Okay? So probabilities need to be the same. That's what this says. If you then want to express the probability density for the field as a function of these field variables, okay, then you can write it as the probability distribution function of the noise, leaving out the arguments of the fields, times j of phi, where this j of phi is the Jacobian of the transformation. So it's the derivative of the noise functional by the corresponding field term. So let me write it out. This j of phi is the determinant of the measure for the noise by the fields. Okay. That's what you have. Good. What I'm not going to do in the lecture is to calculate this Jacobian. You see this in the notes. We will not use it really during the whole calculation. So it would just be sidetracking us quite a bit. So we just leave it. And I'll give you the result. So if you do the math, then you find that the Jacobian is the determinant of the exponential of minus theta times an integral over space and time dA of phi matrix d phi of x and t. Okay? So that's what you do get here. Oh, sorry, this is, of course, also a vector here, and maybe I write it better like so, of beta, then it's clearer what I mean. Good. Now, when we and I'm ignoring this in the following. So basically, you can think of this as me setting theta to 0, but I don't have to. I'm just don't want to complicate matters too much for the analysis that we have. So having that, we then get the functional for the field in a very simple way, right? So when you look at the expressions that we have on the board, then W phi is basically the same as W theta. And what you have to do is here, you have to replace in the theta the corresponding expressions from the Langevin equation. So from here, and connect it to the field. Okay? So that's what I'm doing. I'm just replacing in the noise distribution function the theta by dt phi minus the functional A that describes either model A, B, or some other model. So that then gives you a normalization factor that again has to be chosen such that the integral over 1 is 1. So you have normalization. And then we have here a functional g, which depends on the fields and also on the initial and the final time, where this functional g is given as 1/2 integral over x and t dt phi alpha minus the drift term, the noise amplitude matrix inverse, and dt phi phi beta minus A beta. And if you wonder what this xt means, where do I have it? Yeah, so I'm taking here a shorthand notation. So this lengthy expression that you have here, I'm calling this an integral xt, just to not always write it in this lengthy form. Okay, so that's what we get. And you might recognize this is not really different from what we had earlier for particles, where these were positions for the particles that just now have expressions where these are field variables, and the a's that you have there are functionals instead of just functions. Now, if I would like to calculate the average of an observable, so let's say O of phi is some observable, and this may be the field itself, some square of the field, some other combination, so some functional O of phi. If I want to take the average over the field configuration, I need to do two things. And let me illustrate this here with a diagram. We have here time, t, and here I'm depicting in a very coarse-grained fashion the field as a variable. Here is my initial time, and here is my final time. I'm starting out, say, with some initial field. I'm ending here with some final field value. Of course, those are functions and not values. If I want to average an observable over such a dynamics for the field, I need to sum, right, over all the possible trajectories that get me from one location to the other. That's what I have to sum over, but also, in addition, maybe I should draw this correctly. I have to integrate here over the initial distribution. So initially the system might be in thermal equilibrium or some other kind of steady state, and that's also something that I need to average over. So you have here an initial distribution for the field. For the field phi naught, which is the initial one. For the final one, I don't, because I want to have the average that gets me from a distribution to a particular final field configuration. Okay. So let me write this down first. So integral over d phi naught p0 of phi naught. Then I do have a path integral from phi 0 to phi f. Of course, I should write here vectors for all these objects. I'm integrating over all the different trajectories, so I have a functional integral. Then I want to average over my observable, that is some functional of the field phi. And then I need to multiply this with a measure, and that's my functional g of phi depending on the initial time and the final time. Okay, and now it depends on what we want to know, of what kind of average you want to consider. So here initially you have some distribution, and then the system develops to this particular value, and then you might say, I'm not really interested in what the value actually is, so I'm integrating also over the final configuration. Okay. And that doesn't need to be a distribution function, because given phi naught, I know what phi f is, and then I have to sum over all the possible values that there are. Okay. So what we have is these different integrals. You have an integral over the initial distribution. You have an integral here over the final values. And then in between, so here you have the path integral, and that is this distribution that you have here. Okay, and for that, let me introduce a name. I call this a transition from phi naught to phi f, and I want to average the observable O of phi. Okay? So in a sense, that's the way you should read it. This here is the weight for the corresponding trajectory, so as a propagator, if you like, and then I'm writing this in a bracket notation indicating that this is the operation I want to perform. Questions? Okay, so this G has a name. It is called the Onsager-Machlup functional. And it corresponds to a statistical weight, or let's say e to the minus g is the statistical weight for a field trajectory. Phi of x and t. This is the setup that we would like to use. Now to look at a few things. The first one is going to be the derivation of the fluctuation dissipation theorem, meaning the one that relates the noise amplitudes that you have here to the amplitudes that you might have in the corresponding Langevin equations, so the L alpha and the M's here. All right, so this chapter is called Detail Balance. Time reversal invariance. And let me call this relation between the amplitudes of noise and the Onsager coefficients the Onsager-Einstein relations. So let me draw again a picture that makes this very clear. We have here again time, and here our field variables. we have some initial time and some final time, and we may have some trajectory that brings us from the initial time to the final time forward in time. Now we are in equilibrium, that's what I'm assuming. So assume a thermal equilibrium situation, or meaning I have time reversibility. Forward and backward paths are equally likely. That's what I mean. And if that's the case, right, then for each forward path, there's going to be exactly the same but time reversed path that starts from the final value and ends at the initial value. And the point is that for systems like so, this must be as likely as the forward path. Okay. So forward and backward path are equally likely. The joint probability for that, this is what I mean. So if we write this, the joint probability for the forward path is phi naught t naught phi f tf. And now just to simplify my notation, I'm not going to write the vector errors anymore, but just think of all these fields as vector fields. So this joint probability density I can write, always write, as the conditional probability density that when starting at the initial value phi naught, at some initial time t naught, I'm arriving, conditioned on that, at the field variable phi f at the final time. And then I need to multiply that by the initial distribution function of phi naught. So that's the conditional probability amplitude, and that's the initial probability density. So this is, so to say, what you can do when you want to analyze this on a computer or experimentally. That's the state that you would prepare, the ensemble you would prepare, and then look at the time evolution of that. Okay, so we take now P of phi naught t naught equal to the equilibrium distribution of phi naught. So I'm taking this as 1 over the partition sum, the exponent of minus the inverse temperature times a functional, that's the free energy functional. Okay. So remind you, this is the free energy functional, and set of t is equal to e to the minus beta. And now you have to be careful with what I'm writing here. This is now f of t, this is a calligraphic f. Okay, hope you can write this, I can't. The f of t that we have here is then the actual free energy. Okay, so of the thermodynamic problem in equilibrium, that's not the same object as the free energy functional. The functional describes the statistical weight of a particular configuration. The free energy itself is the free energy as you sum over all the possible states, and that's why this here is the normalization factor of the corresponding probability measure. So the integral over that needs to be 1, so that means the functional integral of that is that, and that you can write as e to the minus free energy. Okay. All right. Now, the way I can write the fact that I have a time reversible dynamics is in two ways. So the simplest way is to say the probability of the forward path is the same as the probability of the backward path, but that's the same as detail balance. Okay. And in this formulation, it's pretty obvious because these expressions for the total probability, they become our transition amplitudes from the state phi naught to phi f, so the integrals over all the trajectories that are confined to start at phi naught and end at phi f. Okay. Remember, that's our definition. This is the constrained path integral where I sum over all the statistical weights conditioned on starting at phi naught and ending at phi f. So this here times p equilibrium of phi naught is the same as going the other way around. So starting at phi f at a equilibrium distribution for phi f and then going backwards to the state phi naught. Okay. Hope that's clear. So this is really the same thing. Time reversibility and detail balance are the same. So here, as we read it out, you start in equilibrium, you go to the final state. This is the same, that's the same likelihood as going the other way around. Good, now let's focus on doing the calculation. So calculating the backward trajectory. So for the backward trajectory, so from the final state to the initial state, I'm going to get there if I reverse the initial forward trajectory. So my forward trajectory was phi alpha as a function of x and t, and I get the reverse trajectory when I start from the final time and I go backward in time. So at t equals 0, I'm now starting at the value phi f, and at t equal tf, I'm arriving at phi initial. So I want this to be the time reverse path, and then I need to account for the fact that there is a parity when I do so. So for fields that are scalar and even under parity, this is 1, and if this is some kind of velocity field, then it would be minus 1. So with epsilon alpha, the parity of the field phi alpha, and I have no sum convention here. This really means for a given alpha, not summed over alpha. Okay, so if I'm now calculating a backward trajectory, so let's say I have a forward trajectory, and now I really want to calculate a trajectory backward. So from here arriving there, this would be the rate of going from the final to the initial state. So for that, I'm getting an integral over all these reversed paths from phi f to phi naught. They start at phi f, but of course I need to multiply with epsilon. So to be precise, this is for each alpha, epsilon alpha, phi f alpha, and I'm going back to phi naught. And I'm integrating then the corresponding Onsager-Machlup functional minus g, where I'm inserting the reversed path. And note that I'm still going from 0 to tf. Okay, I'm not going in another way here, because as I was just explaining, if you look at this, t equals 0 is when you start at the right end, and t equal tf is when you end at the left end. So the integrals appearing in the Onsager-Machlup functional are the same as before. Okay, now let me write this out with the corresponding Onsager-Machlup functional between the initial time point 0 and tf. This is now writing this out explicitly, a function of x and time, and the set time running from 0 to tf. And then I need to write here the temporal derivative of the reversed fields, alpha minus the functionals for the drift, also independence of the reversed, time reversed fields. And then I do have my inverse noise matrix, and here the same expression for the reversed fields, just the other field components, phi r. And again, I'm ignoring the Jacobian, so I'm setting theta equal to 0, since in the end, if you check it, it doesn't really matter for my argument. Now, you can write this, rewrite this back in the following way, and I'll show you in a second how this works. So xt minus epsilon alpha dt phi alpha minus a alpha epsilon phi n alpha beta to the minus 1 minus epsilon beta dt phi beta minus the drift term epsilon phi. So up to the calculation that I'm going to show you in a second, just let us look at what this is. So the reversed path Onsager-Machlup functional looks very much the same, if you look here on the right, as the corresponding Onsager-Machlup functional that we have here. right? And all we have done is that we change the fields to the fields times their parity in the functionals for the drift term. And here, because we have an additional time derivative where t goes to minus t, we have a minus and also the parity times the field. So basically, this reversed, this Onsager-Machlup functional for the reversed fields is one where I'm replacing all the fields on the right-hand side by their corresponding expressions with a parity multiplied. So now let me, as an aside, show you the basic reasoning for that. It's very basic and simple, but let me do it anyway. So if you integrate over time, which is this integral that you have here over time, it's from 0 to tf with some integration variable t dt phi alpha r of t, and then I'm saying here, let's say this is just some function of phi, and this could be either, this multiplying by that, or this term multiplied by this term. So it's just some function f of epsilon phi r of t. Now I'm using my definition of the reverse trajectory, so I insert this expression here on the right-hand side, which means, oh sorry, this is no epsilon yet, this is just phi r. This then means I'm integrating from 0 to tf dt. Okay, let me now insert this. It's epsilon alpha dt phi alpha tf minus t f of epsilon phi of tf minus t. I'm now renaming things. So let me call this here then t twiddle. Okay. If you do so, then this here is also t twiddle, right? The same thing. But now derivative with respect to time, you have to translate this to a derivative with respect to t tilde, which is then dt d minus t tilde. Right? Or like so, right? Same thing. If you look here, this then gets an integral over minus dt twiddle, but you also have to revert from tf to 0 if you do so. And this with that, as you change the integral signs back again, cancels the minus. So this is the same as the integral from 0 to tf dt twiddle. That's the first term here by flipping the integration order. Then I have minus epsilon alpha dt phi alpha of t twiddle, and then f of epsilon phi of t twiddle. Okay, so here we are. That's what I wanted to show you. This is the whole calculation, and then you see that this is this minus that appears when you have a time derivative, and here correspondingly for the function f. Okay, so what we have then in the end of the whole calculation, that this here, this expression that we have, okay, it's actually here, So this expression where I have g of phi r, I'm writing this as gr of phi t naught tf, where you just have to memorize for yourself that the index, the subscript r, means I'm replacing in the original Onsager-Machlup functional all the fields by the fields times the parity, and I change t into minus t. So t to minus t and phi alpha to epsilon phi alpha, that's the meaning of r. Okay, now let's look at our detail balance condition. So remember, this is like final state conditioned on initial state with some initial distribution, e to the minus beta functional f of phi naught. That's my equilibrium distribution. There's also a normalization factor, which I ignore because it's the same on the right and left-hand side. This is then equal to phi 0 conditioned on phi f, and I'm starting at a equilibrium configuration at the final time. And you have to combine this with these probability amplitudes that we have. The forward amplitude is just the original Onsager-Machlup functional. And the backward amplitude we just calculated, this backward amplitude contains the reversed Onsager-Machlup functional. So, and since this is all valid for all the trajectories that we have in mind, I don't pick a particular trajectory. I know that this is going to be valid for any particular trajectory that we have. So that means from that we can actually write that beta f of phi naught, so this term, plus the corresponding propagator that comes here, which is the Onsager-Machlup functional of phi from 0 to tf. That's the left-hand side. And that needs to be equal to what we just calculated, this object here, gr of phi 0 to tf plus beta f of phi f. You can also say this differently. This is the exponential of the statistical weight for the forward path. And this is the exponential for the statistical weight for the backward path. And they need to be the same. And this is, equivalent to time reversal invariance, which is the same as detail balance. So we do have now a formal path integral form of what the implication of time reversal invariance and detail balance mean. You can write this a little differently. So you can also write this as the time reversal operation acting on G of phi 0 tf plus beta f of phi f. Because this time reversal operation does nothing but that. It will replace t by minus t, and it will replace the fields by the fields times their parity. So let us now apply this to a model, namely model A. So you see how this actually gives you a nice way of proving the Onsager-Einstein relation. So let's see how this works out there. For model A, we remember what the Langevin equation is. And then let's just insert this right away. So we have beta f of phi naught. This is this term. Then plus, what do we have? What's the best way of doing this? Yeah, let me go here. So here we have the probability measure for the noise, but that's the same as the probability measure for the fields if you replace the zeta by the equation of motion. So you have 1 over 2n, and that's what you have here because this is a scalar one-component theory. And then you have an integral over space and time. And inserting the equation of motion just means you write L dt phi plus L df d phi. That's the model A expression for the equation of motion. And of course you have a square because it's Gaussian, right? And now this is the same as beta f for the final field configuration plus the same expression 1 over 2n, the same integral over space and time. Now, 5 fields in model A have even parity, so they change to the same variable. There's no sign. But for the first term, changing time to minus time, this is minus dt phi plus L df d phi squared. Okay, this has to be equal. You can square this all out, and then you can cancel a lot of terms. And you can then write this in the following form: beta times the free energy functional of phi naught. This is this term minus that term minus the free energy functional of phi f. That's equal to this right-hand side minus that one. All the terms that are quadratic in each component. So the dt phi squared term cancels. The term which is L df d phi squared cancels. They have the same sign. It's only the mixed terms that survive. So you get 2 times the mixed terms, L over n, integral over df d phi dt phi, integral over x and t. Okay. That's when you get all the terms. And now you have to recall what this object here actually is. Okay, so this is a written out form of the chain rule for a derivative of a functional. So you can write this also as 2L over n. Let me take out the corresponding time integral from 0 to Tf. And then df dt is the same as the integral over space, functional derivative of f with respect to phi, and then you take the chain rule, you multiply by the derivative of the field inside. Okay, but that integral is easy. It's the integral over total derivatives. So that's 2L over n, the free energy functional at the final field minus the free energy functional at the initial field. And now you compare the two sides here on the left and here on the right. They have the same difference of the free energy functionals, and that then means that the prefactors need to be the same. So from that, you do have n is 2LT, which is the Einstein-Onsager relation, relating noise amplitude and Onsager coefficients. And that's similar as we had it before. We did this before using the functional Fokker-Planck equation. This assumes no linearity whatsoever. This is true for any nonlinear type of drift term A of phi. I don't need to linearize that. This is really true in general. Of course, under the assumption that here we used additive noise and not any state-dependent Onsager coefficients or noise coefficients. Right? And that's the typical way you would apply this relation. So you would learn that for any kind of field theory that we have with additive noise, detailed balance or time reversal symmetry implies this equality of statistical weights containing the free energies and containing the propagators and the reverse propagators. And that relation here is then used for different kinds of field theories to derive this noise amplitude Onsager coefficient relation. And you might try it for yourself for model B or for model C or for other kind of models. This calculation is really pretty straightforward.